Here we go. Is there a roller coaster in this particular example, example 4? Then probably I like example 4, I like example 4, I like example 4. This is a nice example of a question that involves momentum, that involves conservation of momentum, that involves energy, conservation of energy. It's kind of cool. It involves roller coasters. And I think the collision-y parts don't have angles. We're not going to be adding things tip to tail. So here's what it says. A roller coaster with an initial velocity VI of 8.6 meters per second, as is obvious from that well-drawn diagram, rolls down a hill. It strikes a second identical roller coaster right here. This identical roller coaster was also already moving at 2.4 meters per second. So I guess this first roller coaster kind of rear ends it and they stick together. How high will they reach up the next hill? I think, Joss, I'm going to argue there's 3 things going on here. The first situation is the first roller coaster going down the hill. Because Ty, I think when it gets to right here, it's going to be going faster. The second thing that's going on here is the collision. Wham, they collide. And then I think the third thing is going to be going up to the top of the next hill. So this question has, count them, 3 parts. How will I solve the first part? Conservation of momentum or conservation of energy? Is there a collision or is there a change in height, change in speed, curvy path? So conservation of energy. So situation number 1, I'm going to start out going KE initial plus PE initial equals KE final plus PE final. The question isn't mentioning heat, so I'm going to ignore heat. Are any of these 0? Are my speeds ever 0? Am I ever at rest? Nope. Oh, got a latecomer coming in. Have to interrupt the lesson. So no heat was mentioned. I think I'm going to ignore that. I don't think any of these are 0 for kinetic energy. In fact, I think the only thing that's 0 is my final potential energy, my final height. So I'm going to get this. A half mv initial squared plus mgh initial equals a half mv final squared. They gave me the mass of the roller coaster, but in this case I didn't need it. And I'm going to do that trick of going times by 2, times by 2, times by 2 to get my 1/2s to cancel. And that's going to give me Vf squared equals Vi squared plus 2Gh initial, which we've kind of seen before occasionally. I want to get the Vf. I want to know how fast the roller coaster is going at the bottom of the hill before it collides with the second roller coaster. I got to get rid of a squared, so we're going to go square root. So we're going to get 8.6 squared plus 2 times 9.8 times 18. Square root of that. Going to be 8.6 squared plus 2 times 9.8 times 18, square root of that. And I'm going to carry some extra sig figs, Robbie, because this is not my final answer. The question wants to know that final height on the right-hand side of the diagram, so I'll keep extra sig figs. I'm going to go 20.65817. In fact, I'll probably use my answer button if I can. But I'm going to write 20.6, what did I say? 5817 meters per second. Okay, there's the first part of this question. Part 2, the collision. Did I say collision? That's a job for conservation of momentum. The sum of all the momentum before equals the sum of all the momentum after. Before the collision, what's moving? Mass 1, mass 2, both, or neither? Stuck together or separate before the collision? So I'm going to have momentum of the first guy initial and momentum of the second car initial. You ready, Drake? Wham! They collide. After the collision, what's moving? I think stuck together both. Inelastic. Now, before I go further, if I wanted to kick this up a notch, how could I do that? Hey, I could have this second roller coaster, instead of moving to the right, I could have it moving to the left. How would I show that? I'd just make its velocity negative. Okay, doable. I guess I could have them not stick together and just ask how high the second car went. I guess. I don't think I will do any of those, but just kind of get your mind thinking about ways we can tweak this. So I said momentum of both. Tori, right here, the ground looks flat. I don't think this collision has angles. Oh, thank goodness. So I don't think I'm going to be adding stuff tip to tail. Oh, thank goodness. I think I can just go straight to solving this algebraically. I can say mass 1 V1 initial plus mass 2 V2 initial equals mass 1 plus mass 2 V final. It's going to be divide by both masses, so it's going to be M1 V1 initial, M2 V2 initial, divided by M1 plus M2. Did I say both cars were the same mass? I can't remember. Yeah. Identical cars, so M1 equals M2 equals 250. Okay. So 250. What's V1 initial? 8.6? Robbie, by far the most common mistake that I see, because you may see this question in the future somewhere, is kids put the 8.6 there. Isn't that the initial velocity? That was at the top of the hill, but that's not the initial velocity in the collision. That's why I had to walk through step 1. I needed to figure out how fast is it going at the bottom of the hill. That's going to be its initial velocity. So I'm going to go 20.65817. Of course, you know I'm going to use my answer button there. Plus 250, and I guess the second car was moving 2.4 divided by 250 plus 250, 500 if I wanted to do that in my head, and I probably could. After the collision, we're going to get bracket 250 times answer button plus 250 times 2.4 divided by, is it okay? I'm going to add that together. 500. And I get, double check my typing, plus and plus times. Do you get 11.5291? I'll write 11.53, but I'm going to keep this number on my calculator as well. Now what? Next step. We're going to go up the hill. Did I say up the hill? I think that means for step 3, there's going to be a change in height and a change in speed and a curvy path. I think this is a job for conservation of energy. Step 3. We're going to go conservation of energy. Kinetic initial, potential initial equals kinetic final plus potential final. Again, the question, Liam, doesn't mention heat, so I can ignore that. Are any of these 0? Mm-hmm. Which ones? Prince Edward Island. And at the top, if I want to figure out how fast, how high I'm going to go for a split second, right there. How many of you have ever been to Knott's Berry Farm before? Okay, so the ride Montezuma's Revenge, which shoots you up a hill, through a loop and up a hill, is kind of an example of how high something goes. There's no collision, obviously, and I don't know of any rides that have a deliberate collision. That would be something going terribly wrong here. But the rest of the physics would be pretty nice to analyze. I'm willing to bet if you measured how high you went, you could calculate your launch velocity. And that's an interesting one as well, because that one launches you from level ground with some kind of either air device or electromagnetic device or something like that, yeah? A half mv initial squared equals mgh final. Now this mass would be the mass of both of them, but the m cancels. And I guess to get the final height by myself, it's going to be vi squared divided by 2g. It's going to be 11.53 squared divided by 2 times 9.8. This number squared divided by 2 times 9.8. And I get 6.78 meters. Woohoo! So we started out with a height of 18 meters, but we lost in that collision there a lot of our velocity, and that meant that we reached a much lower height. Before we turn the page, I would argue, technically, Riley, this is all Physics 11. It's a 3-step complicated question. I don't think I'd throw something like this at my Physics 11 kids. But was there vectors involved here? No, Physics 11. Example 5, a football question. Hey, we're 2 weeks from the Super Bowl. We just had the conference championship games on the weekend. So let's talk football. 100 kilogram, I made up nice round numbers, tied, but this is for my football guys. 100 kilogram fullback is running with a football at 2 meters per second. He's met head on and he sticks to a tackler. So we're going to have it be a straight head on collision, keep the angles out of it. Which tackler is more likely to stop the fullback? A 200 kilogram lineman moving at 1 meter per second, or a 50 kilogram cornerback moving at 4 meters per second? Or both the same? Connor? Convince me. And if I wanted to be fussy, I would say the change in momentum then will be identical, because they'll transfer their momentum to the runner, transferring a positive 200 or a negative 200 to a positive 200. Your final momentum will be 0. They'll be at rest. Okay? We can even, if we want to, write momentum here equals 200 kilogram meters per second. Momentum here equals 200 kilogram meters per second. You know what? In front of that, let's put a negative in front of each of that. Let's make their momentum negative. And this guy has a momentum of positive 200 kilogram meters per second. I made up nice round numbers, Andy, for a reason, because I wanted to get nice 200s. Okay. So this sort of explains, if you watch football, some of the tackling that goes on. If you're bigger, you don't have to move as fast to bring a person to a stop. If you don't weigh as much, you have to be moving faster to bring a person to a stop. Which tackler is going to cause more hurt? The 200 kilogram lineman moving at 1 meter per second, or the 50 kilogram cornerback moving at 4 meters per second, or because they have the same momentum, it's both the same? And convince me. Same momentum? Yeah.
I would argue the one moving faster.
The cornerback? Convince me.
B squared.
Hurt is energy, because hurt is I have to absorb your energy as well, okay? So for hurt, look at kinetic energy, which is a half mv squared. The reason is I know after the tackle, The kinetic energy is gone. It's zero. Now, it can't vanish. Where did it go? I think it would have gone into force times distance. I think, Robbie, force times distance, and the distance is going to be like compressing the ribs or making the guy, moving the person here. Okay? So how much kinetic energy does the lineman have? Well, it's going to be 0.5 times 100 times 1 squared. I'm going to do that in my head. 1 squared is 1 times 100 is 100. Half of 200. 200 kilograms. Half of 200 is what? So the lineman has 100 joules of energy. If I look at how much kinetic energy the cornerback has, it's going to be 0.5 times 50 times 4 squared. 4 squared is 16. Half of 60. What do you get here? How many joules of energy does the cornerback have? 400 joules of energy. That's going to be hurting more. Both collisions will bring the person to a stop. This one, the second collision, would blow the guy up. I mean, it'd be one of those ones where you'd see it on Sports Center as a big tackle. Okay? Using principles of physics, I'm just going to say look at kinetic energy. And yeah, because of the squared. What are the biggest hits? Who delivers the biggest hits? It's either the the slightly lightweight linebacker who can move really fast but still has a fair bit of mass, or for the longest time in the 80s and the 90s, it was the safeties, because often the safeties were former cornerbacks that had gotten a bit older and slowed down a little bit, or former linebackers that had lost a bit of weight and were a little bit faster, so they had most of the speed of the cornerbacks and most of the mass of the linebackers. So if you watch old 80s and 90s football highlights, now they're cutting down on those hits because they've also realized that they're doing damage and concussions and all that, so the rules are changing, and that's probably a good thing as well. But some football physics for you. One more. I think this is the last one. Little note, again, because students often get mixed up the notion of what's conserved and what's not. Energy, total energy is conserved, always, always, always. Kinetic energy is only conserved total momentum is always conserved as well. I should have said that first. So total energy, momentum is conserved. Kinetic energy is only conserved in what we call a perfectly elastic collision, which rarely happens in real life. In other words, kinetic energy is usually not conserved. Usually you lose some kinetic energy. It's transformed into heat and sound and other dissipative energies. So, I like example 6, I like example 6, I like example 6. This is a nice question. Either the colliding roller coasters or something like this, to me, would make a nice Physics 12 combining energy and momentum in one question. I'm not going to give you one where stuff is at angles and combining energy in the same question. I don't think. If I did, it would be a lovely right angle and it'd be easier. It says a cart traveling 2.2 due east. You know what? There's a compass direction, north, east, south, west, collides with a stationary cart and the two stick together. How much kinetic energy was lost during the collision? During the what? During the collision. During the what? During the collision. I think I'm going to be using conservation of momentum and conservation of energy. I think the first thing I want to do here is analyze the collision. I'm going to start out by saying the sum of all the momentum before equals the sum of all the momentum after. I'm going to call the 3.6 kilogram cart, cart 1, and I'll call the 1.5 kilogram cart, cart 2. Before the collision, what was moving? Cart 1. So I'm going to have this. The momentum of cart 1, initial. Second one was stationary. Wham! They collide. After the collision, what's moving? I think here, both stuck together. If they were separate, I would just have two momentums here. Now I pause. Does this question mention angles? Do I have different directions? Do I have a north and an east or a south and an east? So I can go do this algebraically. I don't need to draw this tip to tail. Okay, that's a little nicer. I'm going to get this. Mass 1, V1 initial, when they collide. Mass 1 plus mass 2, V final. I think the final velocity after the collision is going to be m1 v1 divided by m1 plus m2. After the collision, I think it's going to be 3.6 times 2.2 divided by 3.6 plus 1.5. Can I do that one in my head? No, the 3.6 doesn't cancel or anything. Yuck. 3.6 times 2.2 divided by 3.6 plus 1.5. And I get 1.55294. I'm going to go 1.553, but I'll keep this number stored on my calculator. Meters per second. Robbie, that's not what the question asked. What did the question ask? How much
KE
was
lost.
during the collision? Now, how am I going to figure out how much was lost? I think I'm going to figure out how much there was at the start, how much there is at the end, and I think if I subtract. You okay with that? Okay. So, to find KE lost, that's going to be how much KE there was at the start, take away how much KE there was at the end. I'm leaving a big space because I have a feeling I'm going to break these up into stuff. Before the collision, what was moving? Okay, so before the collision, all I have moving is going to be a half mass 1 V1 squared. And that's going to be V1 initial. After the collision, what was moving? Both stuck together or separate? Okay, if they were separate, I would just put both in brackets. I would go a half m1 v squared and a half m2 v squared. Since they're stuck together, I guess I don't really need the brackets. I can go 1/2, but Sinead, I better make very, 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 very sure that I put here, it's the mass of both, and that's going to be v final squared. And I better make sure I get the right masses in for each part. Okay, I think I can do this. The kinetic energy that was lost is going to be 0.5 times 3.6 times 2.2 squared minus 0.5, and then this is going to be 3.6 plus 1.5 times 1.553 squared. The amount of kinetic energy before, take away the amount of kinetic energy after. And even if I had angles in this question, Connor, even if there had been yucky angles on this line here, even if these velocities weren't all east-west, I wouldn't care because energy is a scalar. I wouldn't worry about putting V's negative or positive or 20 degrees what of what. I wouldn't worry about any of that, which is kind of nice. Some of you are typing already. Let's see. 0.5 times 3.6 times 2.2 squared minus 0.5 times 3.6 plus 1.5 times my answer button squared. Do you get 2.56 joules? The kinetic energy lost 2.56 joules. If we had gotten an answer of exactly 0, then we would describe that collision as a perfectly elastic collision. By the way, when they stick together, you tend to lose an awful lot of kinetic energy. When they bounce apart, because now you have two objects moving, you don't lose as much kinetic energy because you've got two objects moving afterwards, but you'll still lose some kinetic energy. Oh, unless you get an answer of 0. If you get an answer of 0, then we call that Not just an elastic collision, but a perfectly elastic collision. That's what was meant by those three types. I'm, again, not going to do a big song and dance or fussy part about a perfectly elastic collision on your test. I'm mentioning it because it's in the curriculum and I'm a nerd. Oh, we got one more. I thought I was done. There is one more. In number 6, oh, no. I guess the only difference, except both cars are moving at the start. Yeah? I think I'm going to pass on that. I think you folks are getting the hang of this, I think. In fact, I probably should have done example 7. I think next year I'll nuke example 6 and I'll go straight to this one. I want to give you time to work on this. I also want to go over your work energy tests. So, what's your homework? A lot of you still are slugging your way through the stuff at angles and work through that. Number 1 is fair game. B says how much work was done during the collision. That's a synonym for how much kinetic energy was lost. They give the answer as a negative because it's lost energy. I think in my method you'll probably get a positive answer. If you solve it in terms of the work energy theorem by going work equals the change in kinetic plus the change in potential, then you'll actually get a negative answer. But if you want to, that's how much work was done, negative 42 joules. You lost 42 joules. If you want to figure out how much kinetic energy was lost, you lost positive 42 joules. So number 1. Number 2 is a ballistic pendulum, except the bullet goes through. See if you can figure that one out. 3 is good. 5 is good. 6 is good. 7 is good. 9 is good. 10, I haven't done explosions yet. Yucky angles. 11 is yucky angles. 12 is a good little thought question.